Albert Einstein and the letter to Roosevelt. In the late 1930s, the world of physics was moving through a quiet revolution. Discoveries about the atom were no longer abstract theories confined to chalkboards and lecture halls. They were becoming real, measurable, and potentially powerful. At the center of this scientific turning point stood Albert Einstein, already one of the most recognized scientists in the world. His name was synonymous with genius, yet the story that connected him to the atomic bomb was not born from ambition or a desire to build weapons. It began with fear, responsibility, and the uneasy awareness that science does not exist in isolation from politics. The discovery of nuclear fission in 1938 by German scientists Otto Hahn and Fritz Strassmann revealed that splitting uranium atoms released enormous amounts of energy. Physicists quickly understood the implication. A chain reaction could produce power on a scale humanity had never seen. Some saw the potential for energy generation, but others immediately recognized the military possibilities. Europe was already under the shadow of rising fascism, and Nazi Germany had demonstrated both scientific capability and aggressive intent. The idea that such a regime might develop an unprecedented weapon deeply alarmed many scientists. Leo Szilárd, a Hungarian physicist who had long contemplated nuclear chain reactions, was among the most concerned. He believed that if Germany succeeded in weaponizing fission, the consequences would be catastrophic. Szilárd knew that his own voice might not carry enough influence with the American government. Einstein, however, had global recognition and moral authority. Though Einstein was a pacifist by conviction, he was also a realist who understood the danger posed by the Nazi regime. When Szilárd approached him in 1939, he brought not just a scientific argument but a warning about the direction of world events. Einstein listened. He had fled Germany himself and was painfully aware of the political climate in Europe. The persecution of Jewish scientists and the militarization of research were not distant rumors to him. They were personal realities. Szilárd explained that uranium could be used to build extremely powerful bombs, and that Germany had already restricted the sale of uranium from occupied territories. This suggested strategic interest. The possibility that the Nazis were moving toward nuclear weapons weighed heavily on both men. The result of their discussion was a letter addressed to U.S. President Franklin D. Roosevelt. Einstein signed it in August 1939. The letter did not contain technical blueprints or dramatic language. It was measured, cautious, and focused on urging the United States to take the potential of nuclear chain reactions seriously. It warned that a new class of bombs might be constructed and that the U.S. should accelerate research into uranium. The message was simple: do not fall behind in a race that could determine global security. Roosevelt received the letter at a time when the United States was not yet fully involved in World War II. Still, the warning was persuasive. Advisory committees were formed, and over time these early steps evolved into what would become the Manhattan Project. Einstein himself did. When bombs were dropped on Hiroshima and Nagasaki in August 1945, the world witnessed the devastating power of nuclear energy used as a weapon. Cities were destroyed, and tens of thousands of lives were lost instantly, with many more affected by radiation. Einstein learned of the bombings like much of the public did through news reports. Though he had feared Nazi development of such weapons, Germany had already surrendered by the time the bombs were used against Japan. In the years that followed, Einstein spoke openly about his regret. He clarified that he did not regret warning the United States about nuclear research itself, but he regretted the necessity of that warning and the path history took afterward. He once remarked that had he known Germany would fail to develop the bomb, he would not have signed the letter. His statement reflected a moral burden rather than technical guilt. He had not built the bomb, yet his influence helped set events in motion. Einstein later became an advocate for nuclear disarmament and international control of atomic energy. He supported organizations that promoted peaceful cooperation and warned about the dangers of an arms race. For him, the atomic age represented a mismatch between human technological power and human political maturity. He believed science had outpaced wisdom. The story of Einstein's letter is not about a scientist turning into a weapons engineer. It is about a moment when knowledge intersected with global crisis. A single document, carefully worded and reluctantly signed, contributed to decisions that reshaped warfare and international relations. Einstein's involvement was brief, but its symbolic weight grew over time. His life remained dedicated to theoretical physics, philosophy, and humanitarian ideals. Yet this episode followed his legacy like a shadow. It demonstrated how even indirect actions by respected figures can ripple through history. The letter to Roosevelt stands as a reminder that scientific insight can carry consequences beyond laboratories, especially when the world is on the brink of conflict. Einstein's regret was not theatrical or exaggerated. It was the quiet reflection of a man who valued peace and understood that knowledge can be used in ways its discoverers never intended. The chain of events that began with concern over Nazi Germany ended by opening the nuclear era. For Einstein, that reality was both a warning and a lifelong lesson about responsibility in science. Leo Szilárd and the nuclear chain reaction. In the early 20th century, physics was uncovering a hidden architecture of reality. Atoms, once thought indivisible, were revealing complex inner structures and unexpected behaviors. Among the scientists drawn to these mysteries was Leo Szilárd, a Hungarian-born physicist with a restless, inventive mind. He was not only interested in understanding nature but also in imagining where scientific ideas might lead. This habit of thinking several steps ahead would define both his brilliance and his burden. Szilárd studied in Berlin during a golden age of physics, surrounded by leading thinkers of the time. He absorbed the culture of deep theoretical inquiry but also developed a practical instinct for applications. Unlike some of his contemporaries who were satisfied with elegant equations, Szilárd often asked what a discovery might mean for society. He sensed early that the energy locked inside atoms was not merely a scientific curiosity. The concept that would change his life came to him in 1933. While walking in London, he was reflecting on recent discussions about nuclear physics and the possibility of releasing atomic energy. The story is often told that he paused at a traffic light when the idea crystallized. If a nuclear reaction could trigger additional reactions, a self-sustaining chain reaction might occur. In theory, this could release enormous energy. It was a simple but profound insight, one reaction causing two causing four, and so on, growing exponentially. At the time, this was speculation. No one had yet demonstrated such a process in a controlled way. Still, Szilárd immediately grasped the implications. A controlled chain reaction might produce power. An uncontrolled one might produce an explosion of unprecedented scale. His imagination moved quickly from laboratory physics to global consequences. Szilárd filed a patent describing the idea of a nuclear chain reaction. Notably, he arranged for the patent to be kept secret by the British Admiralty. This decision already revealed his concern about military uses. He did not treat the idea as a personal asset but as sensitive knowledge. Even before the world fully understood nuclear fission, Szilárd was thinking about security and ethics. When nuclear fission was experimentally confirmed in 1938, Szilárd's earlier insight no longer seemed theoretical. The missing piece had fallen into place. If uranium atoms could be split and emit neutrons, those neutrons could split more atoms. The chain reaction he had imagined was now physically plausible. The scale of potential energy release became a matter of calculation, not fantasy. Europe at that moment was politically unstable and increasingly dangerous. Totalitarian regimes were investing in science, and many scientists had already fled persecution. Szilárd, who was Jewish, understood the threat personally. He worried that Nazi Germany might pursue atomic weapons. His fear was not dramatic or abstract. It was grounded in his understanding of both physics and politics. This concern led him to take action beyond the laboratory. He began urging governments to pay attention to nuclear research. He spoke with fellow physicists and tried to build awareness. Szilárd was not a public figure by nature, but he felt the situation demanded intervention. His sense of responsibility grew alongside the scientific evidence. One of his most consequential steps was helping to draft the famous letter that warned the United States government about the potential of atomic weapons. He knew that his own name lacked political weight, so he sought the support of a more recognized scientist to sign it. The goal was not to build a bomb immediately but to ensure that democratic nations were not caught unprepared if others succeeded first. Szilárd viewed it as a preventive measure in a dangerous world. As the American atomic program developed, Szilárd became involved in nuclear research in Chicago. Their work progressed toward the first controlled nuclear chain reaction. In 1942, this goal was achieved with a reactor built under a stadium at the University of Chicago. The moment proved that a self-sustaining reaction was possible and controllable. It was a historic scientific milestone. It also confirmed that the same principles could be scaled toward weapons. Szilárd's feelings grew increasingly conflicted. He had helped open the door, yet he was uneasy about where the path led. He advocated for transparency among scientists and later pushed for diplomatic approaches to nuclear policy. As the war neared its end, he supported efforts to demonstrate the bomb's power in a non-lethal way rather than using it directly on cities. His proposals did not shape final decisions, but they showed his moral stance. After the war, Szilárd turned more toward biology and public policy. He spoke about arms control and international cooperation. He believed scientists had a duty to consider the social impact of their work. For him, the chain reaction was not only a physical process but a metaphor for how ideas propagate through society, triggering consequences far beyond their origin. Szilárd did not express regret in the form of denying his discovery. He remained proud of the intellectual achievement. His regret was tied to how the knowledge was used and how quickly scientific progress could outpace ethical frameworks. He had foreseen the danger earlier than most, yet foreseeing did not mean he could fully prevent outcomes. His life illustrates a particular kind of scientific conscience. He was neither detached nor purely idealistic. He navigated the tension between discovery and responsibility in real time, without the clarity of hindsight. The nuclear chain reaction stands as one of the most significant concepts in modern history, enabling both nuclear power and nuclear weapons. Szilárd's role in its conception places him at a pivotal point in that history. In quieter moments later in life, he reflected on the unpredictability of innovation. A thought formed during an ordinary walk had helped usher in the atomic age. That transformation of a simple idea into a global force remained both astonishing and sobering. For Szilárd, the lesson was not to halt science but to guide it with foresight and humility. His story carries a calm but persistent message. Knowledge expands quickly, but wisdom must keep pace. The nuclear chain reaction changed geopolitics, energy, and warfare. Behind it was a scientist who imagined the future clearly enough to worry about it, and who spent much of his life trying to ensure that humanity would survive its own discoveries. Andrei Sakharov and the Soviet H-bomb. The mid-20th century was a time when physics stepped out of theory and into history with unusual force. Ideas that once lived quietly in equations began to shape the fate of nations. Among the scientists working at this frontier was Andrei Sakharov, a young theoretical physicist whose life would become closely tied to the most powerful weapon humanity had ever conceived. His journey into thermonuclear weapons was not driven by fascination with destruction, but by a belief that scientific work could protect his country in a dangerous world. Sakharov showed exceptional talent in physics from an early age. He grew up in an environment where education and intellectual discipline were valued, and he developed a calm, analytical temperament. Those who later worked with him often described his quiet focus and ability to think deeply about complex problems. This temperament suited theoretical physics, where progress often comes from patient reasoning rather than sudden inspiration. After World War II, global politics quickly reorganized around nuclear capability. The atomic bomb had already demonstrated that scientific breakthroughs could alter military and diplomatic balance almost overnight. Within the Soviet Union, there was intense pressure to catch up with and eventually match the nuclear strength of rival powers. Scientific institutes were given enormous resources and strict secrecy. Talented physicists were drawn into classified programs where their work was directly tied to national security. Sakharov entered this environment as part of a new generation of scientists. He joined a research group focused on thermonuclear design, where the goal was to move beyond fission bombs toward fusion-based weapons. Fusion, the same process that powers stars, promised vastly greater explosive power. The theoretical challenges were immense. Controlling temperatures, pressures, and reaction conditions that normally exist only in stellar cores. Yet, the political motivation ensured that these problems received sustained attention. One of Sakharov's major contributions was a design concept that helped make a practical hydrogen bomb possible. His ideas played a role in shaping the configuration that allowed fusion fuel to be compressed and ignited. This was not the work of a single person but of teams, calculations, revisions, and tests. Still, Sakharov's theoretical clarity made him a central figure. Colleagues respected his ability to simplify complex physical relationships into workable models. When the first successful thermonuclear tests were conducted, they confirmed that the new class of weapons could exceed previous destructive scales by orders of magnitude. These tests were seen by authorities as strategic achievements. For scientists like Sakharov, however, the results also carried a sobering realization. The energy released was so extreme that it forced a confrontation with the meaning of such power. Numbers on paper had become real shock waves, heat, and long-lasting radiation. At first, Sakharov viewed his work through the lens of deterrence. The prevailing logic suggested that if multiple powers possessed overwhelming weapons, large-scale war might be prevented. In this framework, building the bomb was seen as a way to maintain balance rather than to invite conflict. This reasoning was common among nuclear scientists of the era, who felt caught between political realities and moral concerns. Over time, Sakharov's reflections deepened. He studied the effects of nuclear testing, including radioactive fallout and its impact on human health and the environment. The data showed that even tests conducted far from cities could spread harmful materials across large regions. These were not abstract projections but measurable consequences. The more he learned, the harder it became to separate scientific success from humanitarian cost. His internal shift did not happen in a single moment. It developed gradually as evidence accumulated and as he considered the long-term trajectory of the arms race. Each new weapon invited another, more powerful response. The cycle had its own momentum. Sakharov began to worry that scientific progress in weapons was moving faster than political systems could responsibly manage. Eventually, he started expressing support for arms control and limitations on nuclear testing. This position was sensitive within a system that valued strategic strength and secrecy. Speaking carefully but firmly, he argued that reducing tests could benefit global health and stability. His arguments were grounded not in ideology but in physics and data. He remained a scientist in his method, even as his conclusions carried ethical weight. As years passed, Sakharov became increasingly associated with humanitarian concerns and civil rights. His earlier role in creating powerful weapons gave his later words a particular credibility. He was not an outsider criticizing science. He was one of its key contributors who had seen its consequences from the inside. That perspective shaped the seriousness with which some people regarded his warnings. Sakharov did not deny his participation in thermonuclear development. He understood that history could not be undone. His regret was directed toward the scale of danger such weapons introduced into human affairs. He believed that scientists must think about the broader impact of their work, not only its technical success. This belief did not erase his achievements, but it reframed how he viewed them. His story reflects a quiet tension between duty and conscience. He had worked to strengthen his nation's security during a period of genuine fear and rivalry. Later, he worked to reduce the global risks created by that same competition. Both phases were guided by a desire to protect human life, though they expressed it in different ways. The development of the hydrogen bomb marked a turning point in history, placing civilization under the shadow of weapons capable of immense destruction. Sakharov's role in that development ensures his place in scientific history. His later reflections add another dimension: the recognition that knowledge carries responsibility beyond calculation. In the end, Sakharov's life forms a continuous narrative rather than a contradiction. A physicist helped unlock stellar energy on Earth, then spent years urging caution about its use. His journey shows how a scientist can evolve alongside the consequences of discovery. The thermonuclear age did not only change geopolitics, it changed the people who built it. His legacy remains a reminder that scientific insight can illuminate both possibility and risk. The same mind that helped design a powerful weapon also insisted that humanity think carefully about survival. In that balance between intellect and conscience lies the lasting significance of his story. Arthur Galston and Agent Orange. In the middle decades of the 20th century, plant biology was advancing in ways that promised to transform agriculture. Scientists were learning how light, hormones, and chemical signals influenced plant growth. Laboratories studying crops were not thinking about warfare. They were thinking about yields, food supply, and the biology of living systems. Among the researchers working in this field was Arthur Galston, a plant physiologist whose early experiments focused on how to regulate and accelerate plant development. His work was careful, methodical, and rooted in the hope that science could help feed a growing world. Galston's research in the 1940s examined how certain chemical compounds affected plant growth and flowering. One group of substances, known as growth regulators, could influence how quickly plants matured. In controlled settings, these chemicals offered insight into the internal timing mechanisms of plants. Understanding these processes was valuable for agriculture, since farmers often sought ways to coordinate planting and harvesting cycles. Galston approached the subject as a biologist trying to decode nature's rhythms. During his experiments, he studied a compound related to synthetic plant hormones. In high concentrations, it could cause abnormal growth and even kill plants. In low concentrations, it altered development. This dual effect was scientifically interesting because it showed how dosage could completely change a biological response. At the time, such findings were part of basic research. Many laboratory discoveries never leave academic journals, and there was little reason to expect these results would travel beyond plant science. However, scientific knowledge rarely stays confined to one domain. Governments and military planners also monitored research that might have strategic value. Defoliation, the removal of dense plant cover, had long been considered a possible military tactic because vegetation can conceal movement and supply routes. If foliage could be cleared, visibility would increase. This idea existed well before Galston's work, but advances in herbicidal chemistry made it more feasible. Over time, chemical defoliants were developed and refined by various researchers and institutions. Mixtures containing powerful herbicides were eventually produced and later became known collectively as Agent Orange. These formulations were designed to strip leaves from trees and destroy crops. The intention in military planning was to reduce cover and disrupt food supplies. The scale at which these chemicals might be used was far beyond anything envisioned in a plant physiology lab. When such defoliants were deployed during the Vietnam War, vast forested areas and farmland were sprayed. The environmental impact was immediate and visible. Forests thinned, crops failed, and ecosystems were disrupted. Over time, deeper consequences emerged. Some of the chemicals contained contaminants such as dioxins, which were later associated with serious health risks. These included long-term environmental persistence and potential links to human illness. The issue became not only ecological but humanitarian. Galston was deeply troubled when he learned how herbicidal research had been adapted for large-scale military use. His original work had not created Agent Orange itself, nor had he designed it for warfare. Yet he recognized that foundational research, including studies like his, contributed to the scientific base that made such agents possible. For a scientist who valued life sciences, seeing plant biology connected to environmental and human harm was distressing. Rather than remain silent, he spoke publicly about his concerns. He argued that the widespread use of defoliants posed risks that were not fully understood. He called for careful evaluation of environmental and health consequences. At a time when questioning military-related science could be sensitive, his stance reflected a strong sense of responsibility. He believed that scientists should not disengage once their work left the lab. They should remain attentive to how it was applied. His advocacy contributed to broader discussions about chemical use in warfare and environmental protection. These conversations were part of a growing global awareness that technology could have hidden costs. Scientific progress was no longer viewed only through the lens of innovation but also through the lens of impact. Galston emphasized that altering ecosystems on a large scale could produce ripple effects lasting decades. Importantly, his regret was not about studying plant hormones. He continued to value fundamental research and education. His concern centered on application without sufficient ethical and ecological consideration. He saw how easily beneficial knowledge could be redirected under political or military pressure. That realization shaped his later views on scientific responsibility. Galston also encouraged students and colleagues to think broadly about the implications of their work. He supported the idea that scientific training should include ethical reflection. For him, this was not philosophy detached from practice. It was a practical necessity in a world where discoveries could be scaled rapidly. A chemical tested on a few plants in a greenhouse could, under different circumstances, be produced by the ton and dispersed across landscapes. The story illustrates how indirect connections can still feel personal to a scientist. Galston did not mix the chemicals that were sprayed, nor did he plan their deployment. Yet he felt a moral weight because his field helped make such tools conceivable. His response was to advocate for caution, transparency, and environmental awareness. In later years, discussions about herbicides, pollutants, and ecological health grew more common. Public understanding of environmental science expanded, and regulations in many countries became stricter. While these changes had many causes, voices like Galston's played a role in shaping the conversation. He represented a scientist willing to reflect on consequences rather than focus only on discovery. His story unfolds quietly compared to dramatic tales of weapons physics, but it carries a steady lesson. Scientific knowledge moves across boundaries. A finding in botany can influence agriculture, industry, or military planning. Once knowledge exists, its path is not fully controlled by its discoverer. Recognizing this reality can be sobering. Galston's legacy is therefore twofold. He contributed to plant science, and he also contributed to the dialogue about ethical responsibility in research. His regret did not erase his work. It gave it context. It showed that conscience can remain active long after experiments conclude. In the calm, reflective tone that marked much of his career, he treated this history as a reason for greater care, not for abandoning science. The development and use of powerful herbicides revealed how closely human decisions and scientific tools are intertwined. For Galston, the enduring message was simple. Understanding nature brings power, and power requires foresight. Paul Hermann Müller and DDT. In the early 20th century, chemistry was increasingly seen as a tool to solve practical problems. Infectious diseases, crop failures, and insect-borne illnesses affected millions of people worldwide. Scientists searched for compounds that could protect food supplies and reduce the spread of disease. Within this context, laboratory chemistry was closely tied to public health and agriculture. The goal was not abstract discovery but tangible improvement of human life. Paul Hermann Müller grew up with a strong interest in how chemical substances interact with the natural world. Trained as a chemist, he developed a reputation for patience and precision. He worked in industrial research, where the task was often to find compounds with specific useful properties. This kind of work required testing many substances systematically, observing small effects, and refining formulas step by step. Progress was usually slow and built on careful repetition. One of the major problems of the time was the control of insects that carried disease. Malaria, typhus, and other illnesses spread through insect vectors and posed serious threats in many regions. Traditional control methods were limited in effectiveness. Some natural substances helped, but they often broke down quickly or worked only in narrow conditions. Chemists believed a synthetic compound might offer longer-lasting protection. Müller focused on identifying chemicals that were toxic to insects but relatively stable in the environment. After testing numerous candidates, he found that dichlorodiphenyltrichloroethane, later known simply as DDT, had remarkable insecticidal properties. Even small amounts were highly effective at killing a wide range of insects. Just as important, the compound persisted on surfaces for long periods, continuing to work after application. At the time of its discovery, this persistence looked like a major advantage. A substance that did not degrade quickly meant fewer applications and broader protection. Early results showed strong success in reducing insect populations. In controlled use, DDT helped limit the spread of diseases in certain settings. During periods of global conflict and hardship, tools that protected soldiers and civilians from epidemics were valued highly. The compound gained a reputation as a scientific breakthrough. DDT began to be used in agriculture and public health campaigns. Fields were sprayed to protect crops, and programs targeted disease-carrying insects in affected regions. Reports from the early years emphasized effectiveness. In many places, reductions in insect-borne illness were recorded. From the perspective of the era, DDT seemed like a triumph of chemistry applied to human welfare. Müller himself viewed the discovery through this humanitarian lens. He believed that reducing disease and protecting food supplies were worthy goals. His work earned recognition in the scientific community, and he was respected for the practical impact of his research. The narrative around DDT in its early phase was largely optimistic. It fit a broader belief that science could solve long-standing natural challenges. Over time, however, observations accumulated that complicated this picture. Because DDT was so stable, it did not disappear after use. Instead, it lingered in soil and water. Scientists began noticing that it could accumulate in the tissues of animals. Small concentrations taken up by insects could move through the food chain. Predatory birds and other wildlife sometimes showed unexpected effects linked to chemical exposure. These findings did not emerge all at once. They appeared gradually as more environmental data were collected. The very property that made DDT attractive, its persistence, also meant it could spread beyond intended targets. Ecosystems are interconnected, and a compound introduced in one place could travel in subtle ways. This realization marked a shift in how people thought about chemical control. Müller lived long enough to see the debate around DDT become more complex. While he emphasized its role in combating disease, he also acknowledged that any powerful tool required careful management. His regret, as described by those who studied his life, was not about discovering an insecticide but about the unforeseen scale and manner of its use. A compound designed for targeted benefit had, in some contexts, been applied broadly without full understanding of ecological consequences. The story highlights a recurring theme in scientific history. Effectiveness in one dimension can reveal risks in another. A laboratory measures toxicity and stability under controlled conditions, but the natural world introduces variables that are harder to predict. Soil chemistry, water flow, animal metabolism, and long food chains all influence outcomes. These systems respond over years and decades, not just weeks. As environmental awareness grew in the mid-20th century, discussions about pesticides and pollutants became more prominent. Researchers from multiple disciplines, biology, ecology, chemistry, contributed data. The conversation was not about rejecting science, but about refining its application. Regulation, monitoring, and selective use became part of the response in many countries. Müller's personal legacy sits at the intersection of benefit and caution. He contributed to a tool that, in certain contexts, helped reduce suffering from disease. At the same time, the broader environmental effects demonstrated that success in chemistry must be evaluated over long time horizons. A compound can solve an immediate problem yet introduce slower, less visible challenges. His career reflects the mindset of his era, when optimism about chemical solutions was strong. Scientists were addressing urgent needs with the knowledge available to them. Later generations, with more ecological data, reassessed some of those solutions. This does not erase the original intentions. It adds layers of understanding. In a calm historical view, the development of DDT shows how science evolves. Early praise can give way to critical review as evidence grows. Responsible science includes this willingness to reevaluate. Discoveries are not frozen in their first interpretation. They are tested by time and by wider observation. Müller remained, at his core, a chemist who believed in practical contributions to society. The mixed legacy of DDT does not turn his work into a simple tale of error. Instead, it illustrates how powerful tools demand equally powerful foresight. Chemical knowledge can protect life, but it must be guided by long-term awareness of environmental systems. The narrative ends not with a dramatic reversal but with a quiet lesson. Scientific discovery opens doors. How widely those doors are opened, and how carefully people walk through them determines the outcome. DDT's history became one of the early reminders that human health and environmental health are deeply connected, and that chemistry operates within the larger balance of nature. Egas, Moniz, and the lobotomy. In the early 20th century, medicine faced a difficult reality in the treatment of severe mental illness. Psychiatric hospitals across Europe and North America were overcrowded, and effective therapies were limited. Many patients with schizophrenia, severe depression, or chronic psychosis spent years institutionalized with little improvement. Doctors worked with the tools they had, sedatives, physical restraints, and early forms of psychotherapy, but outcomes were often poor. Within this atmosphere, the search for more decisive treatments intensified. Egas Moniz began his career as a physician and neurologist with a strong academic reputation. He was known for his intelligence, discipline, and willingness to explore new ideas. Before his association with psychosurgery, he had already made contributions to neurology, including work in cerebral angiography, a technique for visualizing blood vessels in the brain. His background placed him at the intersection of brain science and clinical medicine, where questions about the biological basis of behavior were actively debated. At the time, many researchers believed that certain mental illnesses might be linked to fixed patterns within the brain's neural circuits. The brain was increasingly viewed as an organ whose structure influenced thought and emotion. If abnormal patterns could be altered, some theorized, perhaps symptoms could be relieved. This idea did not arise from cruelty but from a biological model of mental disease that was gaining traction. Moniz became interested in reports suggesting that behavioral changes could follow brain injuries or surgeries affecting the frontal lobes. The frontal lobes were associated with personality, decision-making, and emotional regulation. Some clinicians observed that damage in these areas sometimes reduced agitation or emotional intensity. To Moniz, this hinted at a possible therapeutic pathway, though the science was still very uncertain. In the 1930s, he developed a procedure that later became known as a prefrontal lobotomy. The basic concept was to sever certain connections in the frontal lobes, with the aim of disrupting pathological thought patterns. The earliest versions involved injecting alcohol or using surgical instruments to affect brain tissue. Moniz reported that some patients appeared calmer or less distressed afterward. These early results were interpreted by supporters as promising. It is important to understand the medical context of that era. Ethical standards, imaging technology, and neurological knowledge were far less developed than today. There were no modern brain scans to guide interventions. Many psychiatric patients were living in conditions that were themselves distressing. In that environment, a procedure that seemed to reduce suffering could quickly attract attention. Moniz presented his findings to the medical community, and the idea of psychosurgery spread. Some doctors viewed it as a breakthrough for otherwise untreatable conditions. The procedure began to be adopted in different countries, sometimes with variations in technique. Reports of improvement in certain patients encouraged further use, though follow-up methods were inconsistent by modern standards. Over time, a more complicated picture emerged. While some patients became calmer, others experienced serious side effects. These could include personality changes, reduced initiative, emotional blunting, and cognitive impairment. The operation did not target a precise lesion. It altered brain tissue in a broad way. As more cases accumulated, it became clear that outcomes varied widely. Moniz himself believed he was helping patients who had few alternatives. He framed the procedure as a medical intervention aimed at relief from severe psychological suffering. There is little evidence that he intended harm. However, intention and outcome do not always align in medicine, especially when knowledge is incomplete. The limits of early neuroscience meant that long-term consequences were not fully predictable. As decades passed, psychiatry evolved. New medications, improved therapy approaches, and better understanding of brain function changed treatment standards. What once seemed innovative began to look crude compared to emerging options. The irreversible nature of lobotomy drew increasing criticism. Many in the medical field reconsidered its value and ethics. Moniz lived during the period when lobotomy moved from experimental idea to controversial practice. Accounts of his later views suggest a more cautious tone about the procedure's application. Whether framed as regret or sober reflection, there was recognition that the method had limits and risks. Medicine, after all, advances by learning from both successes and mistakes. The history of lobotomy also reveals how quickly medical practices can spread when hope is scarce. Doctors facing desperate cases may adopt new techniques faster than evidence can fully support. This is not unique to one era. It is a recurring pattern in medical history. Lobotomy became a lesson in the need for rigorous testing, long-term follow-up, and ethical safeguards. Moniz's broader career reminds us that scientists and physicians are often shaped by the knowledge available in their time. He was neither a villain nor a miracle worker, but a researcher navigating uncertainty. His work emerged from a genuine desire to address suffering, even if the method later proved deeply flawed. Today, lobotomy stands as a historical example rather than an accepted treatment. It is studied to understand how medical ideas develop and how standards improve. The story encourages humility in science. What appears promising under one framework may look very different under another as data accumulates. The narrative of Moniz and lobotomy unfolds quietly, without dramatic twists, but with lasting implications. It shows how the brain's complexity resists simple solutions. Intervening in neural systems affects the core of human personality and identity. Such interventions demand extraordinary care. In reflecting on this history, the central theme is responsibility. Medical innovation carries weight because it touches human lives directly. Moniz's story illustrates both the drive to heal and the importance of restraint. Progress in medicine is real, but it is built on continuous questioning and revision. His legacy, viewed calmly, is part of the larger evolution of neuroscience and psychiatry. Each generation inherits lessons from the last. The era of lobotomy contributed to stricter ethics, better research standards, and deeper respect for the brain's intricacy. From that perspective, even controversial chapters can shape safer futures. Walter Freeman and the ice pick lobotomy. In the mid-20th century, psychiatry stood at a crossroads between hope and limitation. Mental hospitals were filled beyond capacity, and many patients lived for years with severe conditions that resisted available treatments. Doctors faced daily scenes of distress, agitation, and suffering, often with few effective tools to offer relief. Sedatives could calm symptoms temporarily, but they rarely changed long-term outcomes. In this environment, some physicians searched for bold interventions that might succeed where traditional care had failed. Walter Freeman was originally trained in neurology and developed a strong interest in psychiatry. He was an energetic communicator, confident in his ideas and skilled at presenting them to both medical audiences and the public. Unlike many researchers who stayed within laboratory or hospital settings, Freeman believed in actively promoting treatments he thought beneficial. His personality played a major role in how his methods spread. Freeman became interested in psychosurgery after learning about earlier lobotomy techniques developed in Europe. Those procedures required drilling into the skull and were performed in operating rooms by surgeons. Freeman, however, was not a trained neurosurgeon. He collaborated at first with surgical partners, but over time he sought a method that would be faster and more accessible. He believed that simplifying the procedure could allow more patients to receive treatment. This motivation led to what became known as the transorbital lobotomy, often called the ice pick lobotomy. The name came from the instrument's resemblance to an ice pick, though it was a medical tool designed for the procedure. Instead of opening the skull, the method involved inserting a slender instrument above the eye socket, passing through the thin orbital bone, and moving it within the frontal lobe to sever neural connections. The procedure was brief and did not require a traditional operating theater. Freeman presented this approach as practical and efficient. He argued that it reduced the need for complex surgery and could be performed in psychiatric hospitals. In an era when resources were stretched thin, this practicality appealed to some institutions. The procedure spread during the 1940s and 1950s, a period when psychiatric medicine was still developing its scientific foundations. Some patients did appear calmer after the operation. Agitation and severe emotional distress could diminish. For families and hospitals overwhelmed by difficult cases, these changes sometimes looked like improvement. Freeman documented cases and publicly described positive outcomes. His optimism helped build attention around the method. However, the brain is not a simple system, and altering it can produce wide-ranging effects. As more lobotomies were performed, troubling patterns emerged. Many patients experienced profound personality changes. Some became emotionally flat, less motivated, or cognitively impaired. Others lost aspects of independence or social functioning. The very traits that make a person unique, initiative, emotional depth, decision-making, could be altered. Freeman remained convinced for a time that the benefits outweighed the harms, especially in the most severe psychiatric cases. He viewed the procedure as a humanitarian option compared to lifelong institutionalization. Yet, the variability of outcomes made the practice controversial. Not every patient improved, and some were clearly worse off. Another factor shaping the story was Freeman's determination to popularize the technique. He traveled widely, demonstrating the procedure and encouraging its adoption. This visibility increased the number of operations but also drew scrutiny. Critics argued that the method was being used too broadly and sometimes without rigorous evaluation. Medical standards for controlled studies and informed consent were still evolving, and oversight was inconsistent. By the late 1950s, psychiatry began to change. New antipsychotic and antidepressant medications appeared, offering non-surgical ways to manage symptoms. These drugs did not cure mental illness, but they reduced agitation and psychosis for many patients. As pharmaceutical treatments improved, the justification for irreversible brain procedures weakened. Professional opinion gradually turned against lobotomy. Hospitals reduced its use, and ethical concerns grew stronger. Freeman himself faced increasing criticism. Some accounts from his later years describe a more subdued tone when discussing psychosurgery. Whether framed as regret or recognition of limits, there was awareness that the procedure had caused harm alongside any benefits. The story of the ice pick lobotomy is not only about one doctor but about a period in medical history. It reflects how urgency, limited options, and optimism about new techniques can combine to accelerate adoption. When dealing with the brain, the organ of personality and identity, the margin for error is especially small. Interventions that seem promising can carry deep risks. Freeman did not begin his work with cruel intentions. He believed he was addressing real suffering. Yet conviction alone cannot guarantee good outcomes. Medicine advances through evidence, peer review, and long-term follow-up. The lobotomy era helped reinforce the importance of these safeguards. In historical perspective, this chapter contributed to stronger ethical standards in psychiatry. Requirements for consent, oversight, and clinical trials became more central partly because earlier practices revealed the dangers of moving too quickly. The field learned, sometimes painfully, that the desire to help must be balanced with caution. Freeman's legacy is therefore complex. He was a figure of confidence and ambition who pushed a controversial method into mainstream awareness. His work is now studied as a warning about the risks of oversimplifying the brain and overestimating early results. At the same time, it shows how physicians respond to the pressures of their era. The quiet lesson that remains is about humility. The human brain contains billions of interconnected neurons shaping thought, memory, and emotion. Altering that network is never trivial. Treatments must respect that complexity. History remembers the ice pick lobotomy not as a solution, but as a reminder that progress in mental health care requires patience, evidence, and deep ethical care. In the calm arc of medical history, Freeman's story stands as a reflective point. It illustrates how science and medicine grow through correction as well as discovery. Each generation inherits knowledge but also responsibility to question, to test, and to protect the people medicine is meant to serve. Vincent Schaefer and cloud seeding. In the 1940s, atmospheric science was still a young field. Meteorology relied heavily on observation, basic instruments, and pattern recognition. Weather was something people predicted, not something they expected to influence. Storms, droughts, and snowfall were treated as forces of nature beyond human control. Yet within research laboratories, a small number of scientists were beginning to wonder whether clouds themselves might be physically altered under the right conditions. Vincent Schaefer did not begin his career with the goal of controlling weather. He was a chemist by training and a careful experimentalist by temperament. He worked for General Electric in its research laboratories, where scientists were encouraged to explore both theoretical and applied problems. Industrial laboratories at that time often supported curiosity-driven experiments because breakthroughs could lead to future technologies. Schaefer developed an interest in atmospheric processes partly through collaboration with colleagues who studied ice formation. One practical question was how ice accumulated on airplane wings, a serious safety concern for aviation. Understanding how ice crystals formed in clouds could help engineers reduce risk for pilots flying through cold, moist air. This line of inquiry connected laboratory chemistry with real atmospheric conditions. In 1946, Schaefer conducted a series of experiments using a home freezer as a small simulation chamber. He introduced supercooled air and moisture into the cold environment to observe how ice crystals formed. During one experiment, he dropped a small piece of dry ice into the chamber. Dry ice, being extremely cold, rapidly cooled the surrounding air. Almost immediately, he observed the sudden formation of countless tiny ice crystals. The effect was striking because it showed how a temperature change could trigger crystallization in moist air. This moment suggested a larger possibility. If ice crystals could be stimulated in a controlled space, perhaps similar processes could occur in real clouds. Many clouds contain supercooled water droplets, liquid water existing below freezing temperature. These droplets remain liquid because they lack a nucleus around which to freeze. If such nuclei were introduced, ice formation could begin, potentially leading to precipitation. Schaefer moved from the freezer to field experiments. He and his colleagues arranged tests in which small amounts of dry ice were dispersed into clouds from aircraft. When conditions were suitable, they observed increased ice crystal formation and, in some cases, snowfall. The principle became known as cloud seeding, introducing substances into clouds to encourage precipitation. The science relied on microphysical processes rather than dramatic weather control. It was about influencing probability, not commanding storms. The early results attracted attention. In a world concerned about droughts, agriculture, and water supply, the idea of influencing rainfall was compelling. Governments, farmers, and water managers saw potential benefits. Research programs expanded, and different seeding materials, such as silver iodide, were studied for their ability to act as ice nuclei. The work remained grounded in physics and chemistry, focusing on how particles interact with moisture in clouds. Schaefer himself approached the discovery with scientific caution. He understood that the atmosphere is a complex system influenced by temperature gradients, air currents, humidity, and geography. A cloud is not a laboratory chamber. Even if seeding could trigger ice formation, the broader weather outcome depended on many variables. He emphasized that cloud seeding could not create storms from clear skies or guarantee rainfall on demand. As cloud seeding projects expanded, public perception sometimes grew more ambitious than the science justified. Some people imagined reliable weather control, while others worried about unintended consequences. If one region encouraged rainfall, would another receive less? If snowfall were increased in one area, how might that affect downstream water systems? These questions highlighted how interconnected atmospheric processes are. Schaefer grew increasingly aware of these complexities. His regret, as later described by those who studied his career, was not about discovering how ice crystals form, but about how the idea of weather modification could be oversimplified. He saw that public and political expectations sometimes outpaced scientific certainty. Weather systems operate on regional and global scales, and small interventions do not override natural dynamics. There were also geopolitical dimensions. During the mid-20th century, interest in environmental modification extended into military and strategic thinking. The possibility that weather techniques could be used tactically raised ethical and diplomatic concerns. While Schaefer's own work focused on physical processes, he recognized that once a technique exists, its applications are not controlled solely by its discoverer. Throughout his life, Schaefer remained a scientist committed to careful measurement. He continued studying atmospheric physics, emphasizing observation and evidence. He did not present cloud seeding as a miracle solution but as a tool with limited, condition-dependent effects. His perspective was grounded in respect for the atmosphere's scale and complexity. The broader scientific community gradually developed a nuanced view of cloud seeding. Under certain conditions, it can influence precipitation patterns, but results vary and require rigorous evaluation. Long-term climate patterns are driven by forces far larger than localized seeding efforts. This understanding aligned with Schaefer's cautious outlook. His story reflects a familiar pattern in scientific history. A discovery made in pursuit of basic understanding opens doors to application. Society, facing real needs, explores those applications. Expectations rise, and only over time does a balanced picture emerge. The gap between possibility and predictability becomes clearer through data and repetition. Schaefer's legacy is therefore tied to both innovation and humility. He demonstrated that human intervention can interact with natural processes, but he also showed that nature retains its complexity. Clouds are shaped by physics on scales ranging from microscopic particles to continental air masses. Influencing one part does not mean controlling the whole. In a calm historical perspective, cloud seeding represents an attempt to cooperate with atmospheric processes rather than dominate them. The technique relies on understanding how water changes phase and how particles serve as nuclei. These are subtle mechanisms, not dramatic levers. Schaefer appreciated this subtlety and encouraged realistic expectations. His reflections underscore a steady lesson. Scientific capability grows step by step, but nature operates as a system. Discovering a mechanism does not grant mastery over all outcomes. Responsible science communicates limits as clearly as possibilities. Schaefer's work helped expand meteorology while also reminding researchers to remain measured in their claims. The narrative of cloud seeding is not one of controlling the sky but of learning how delicate atmospheric balances are. Schaefer's contribution opened a field of study that continues to be researched carefully. His cautious stance toward overpromising stands as part of his legacy. It shows that discovery and restraint can coexist, and that respect for complexity is itself a form of wisdom in science. Djerassi and the birth control pill. In the middle of the 20th century, chemistry and medicine were increasingly intertwined. Laboratories were not only places for understanding molecules but also for shaping how people lived. Antibiotics had already shown that chemistry could transform public health. Hormone research was opening new doors in endocrinology, revealing how small biochemical signals could regulate major functions in the human body. Within this scientific landscape, reproductive biology became an area of intense interest. Djerassi was trained as an organic chemist, a discipline focused on building and modifying complex molecules. His strength lay in understanding how slight structural changes could alter a compound's biological effect. This kind of expertise was essential in steroid chemistry, where hormones share similar frameworks but produce very different outcomes. Djerassi developed a reputation for precision and creativity in molecular design, qualities that positioned him well for pharmaceutical research. During the 1950s, scientists were studying progesterone and related hormones for their role in ovulation and pregnancy. It was known that progesterone could prevent ovulation, but obtaining it in large quantities and delivering it effectively posed challenges. Natural extraction was expensive and inefficient. Chemists therefore searched for synthetic pathways to create similar compounds that were stable and active when taken orally. Working with colleagues in a pharmaceutical research environment, Djerassi contributed to the synthesis of a compound called norethindrone. This synthetic progestin showed strong biological activity and, importantly, could be effective when taken by mouth. That property made it a practical candidate for a contraceptive pill. The achievement was not a single dramatic moment but the result of systematic chemical work, testing, and refinement. The development of what became the oral contraceptive pill involved multiple scientists, clinicians, and advocates. Djerassi's role was primarily on the chemical side, making the molecule possible. Clinical researchers later tested formulations and dosing. Still, without a reliable synthetic hormone, the entire concept would have remained theoretical. His contribution helped turn hormonal contraception into a feasible medical product. When the first birth control pills became available, their impact extended far beyond medicine. For many women, Reliable contraception meant greater control over family planning, education, and careers. Social structures that had long linked womanhood closely to continuous childbearing began to shift. The pill became associated with broader cultural changes, including evolving discussions about gender roles and personal autonomy. Djerassi recognized that the scientific success carried social weight. He sometimes referred to himself, with a mix of humor and seriousness, as a mother of the pill, acknowledging both the collaborative nature of the work and its influence. Yet his reflections over time revealed a thoughtful awareness of unintended consequences. Scientific tools do not enter a vacuum. They interact with culture, policy, and human behavior. One area of concern was how access and responsibility were distributed. In many societies, the burden of contraception fell primarily on women. While the pill offered freedom, it also introduced expectations and pressures. Djerassi noted that technological solutions do not automatically resolve social inequalities. A molecule can change biology, but it cannot by itself create fairness in relationships or healthcare systems. There were also medical considerations. Early versions of the pill contained higher hormone doses than many modern formulations. As data accumulated, researchers worked to reduce side effects and improve safety profiles. This process illustrated how pharmaceutical science evolves. Initial breakthroughs are followed by refinement. Djerassi understood that long-term monitoring is part of responsible medical innovation. Another dimension was demographic. Widespread contraception influenced population trends in various countries. For policymakers, this raised questions about planning, economics, and public health. For individuals, it changed life trajectories in personal ways. Djerassi observed that a chemist working at a laboratory bench could indirectly influence global patterns. That realization was both impressive and sobering. Importantly, Djerassi did not express regret about enabling contraception itself. He supported reproductive choice and scientific progress. His more nuanced regret related to how society sometimes oversimplified the pill's role, treating it as a complete solution to complex social issues. He emphasized that education, healthcare access, and cultural context matter alongside technology. Later in life, Djerassi turned significant attention to writing and public dialogue. He explored how science interacts with society, ethics, and personal identity. This shift did not mean he left science behind. Rather, he expanded the conversation around it. He believed scientists should engage with the human dimensions of their work, not only the technical aspects. The story of the birth control pill demonstrates how chemistry can intersect with daily life on a profound scale. A synthetic pathway in a laboratory contributed to changes in family structures, workforce participation, and personal planning. Few scientific developments have woven so deeply into social fabric. That depth explains why the pill is discussed not only in medical journals but also in history and sociology. Djerassi's perspective remained characteristically analytical. He saw discovery as a starting point, not an endpoint. Once a technology exists, society decides how to integrate it. Scientists can inform and advise, but they do not control every outcome. Recognizing this limit is part of scientific maturity. From a calm historical view, his work represents the dual nature of innovation. On one side lies clear benefit, expanded reproductive control and medical progress. On the other lies complexity, cultural debates, ethical questions, and health considerations. Holding both sides in mind leads to a balanced understanding. His legacy, therefore, includes both molecular achievement and intellectual reflection. He helped create a compound that altered millions of lives, then spent years thinking about what that alteration meant. This combination of technical skill and philosophical awareness is relatively rare and gives his story particular depth. In the steady arc of scientific history, the birth control pill stands as an example of how a small chemical structure can influence global society. Djerassi's role in that history connects the precision of organic chemistry with the broad currents of social change. His reflections encourage a simple but enduring principle. Scientific power should be accompanied by thoughtful engagement with its human effects. The narrative ends quietly, without dramatic reversal. A chemist solved a molecular problem and later considered its societal ripples. That pattern, discovery followed by reflection, captures the evolving responsibility of modern science. Frederick, Banting, and Insulin. In the early 20th century, a diagnosis of diabetes often carried a grim outlook. Without an effective treatment, many patients, especially children with what is now known as type 1 diabetes, faced severe weight loss, weakness, and ultimately death. Physicians tried strict diets that drastically limited sugar and calories, sometimes prolonging life briefly but rarely restoring health. Hospitals and families watched the disease progress with limited means to intervene. Within this medical reality, the search for a physiological explanation became urgent. Frederick Banting began his career as a physician with surgical training, not as a celebrated researcher. He was practical, disciplined, and familiar with the realities of patient care. Unlike laboratory scientists who worked primarily with theory, Banting encountered illness directly in clinics. This exposure shaped his motivation. He was interested in solutions that could tangibly change outcomes for patients, not only in abstract knowledge. At the time, scientists already suspected that the pancreas played a role in blood sugar regulation. Previous experiments had shown that removing the pancreas in animals led to diabetic symptoms. The challenge was isolating the specific internal secretion responsible for controlling glucose. The pancreas also produced digestive enzymes that could destroy delicate compounds during extraction, making the task technically difficult. Banting's key idea was rooted in careful reading and persistence. He considered whether tying off certain pancreatic ducts might allow the digestive parts of the organ to degenerate while leaving the internal secretion-producing cells intact. If so, an extract from that tissue might contain the anti-diabetic factor in a more usable form. The concept was simple in outline but demanding in practice. He pursued this idea at the University of Toronto, where he gained access to laboratory space and support. There he worked closely with assistant Charles Best and under the broader guidance of senior researchers. The experiments involved operating on animals, monitoring blood sugar levels, and preparing pancreatic extracts. The work required long hours, repeated trials, and careful measurement. Progress came gradually rather than through a single dramatic breakthrough. Eventually, their extracts showed the ability to reduce high blood sugar in diabetic animals. This result suggested that they were approaching the elusive internal secretion. Further refinement improved purity and consistency. The step from animal experiments to human treatment required caution, but the worsening condition of some patients created urgency. When insulin, named from the Latin insula, meaning island, referring to the pancreatic islets, was first administered to human patients, the results were striking. Individuals who had been weak and deteriorating began to regain strength. Blood sugar levels fell toward safer ranges. Symptoms that once signaled decline started to reverse. For families and physicians accustomed to limited hope, these changes felt extraordinary. The introduction of insulin did not cure diabetes, but it transformed it from a rapidly fatal disease into a manageable chronic condition. Patients still needed careful dosing, dietary awareness, and medical supervision. Yet the difference between inevitable decline and sustained life was profound. Hospitals that once focused on end-of-life care for diabetic children could now support long-term treatment. Banting's reaction to success was notably grounded. He did not frame the discovery as a personal triumph alone. He recognized the collaborative nature of the work and the importance of making treatment accessible. He supported the idea that insulin should be widely available rather than restricted for profit. This stance reflected a humanitarian perspective shaped by his medical background. As insulin production expanded, pharmaceutical methods improved purification and scaling. What began as fragile laboratory extracts became standardized medication. Over time, formulations evolved, delivery methods improved, and monitoring techniques advanced. The therapy grew safer and more precise with decades of research. The original discovery opened the door for all these refinements. Banting's later reflections revealed a thoughtful awareness of complexity. He understood that a powerful therapy also creates responsibility. Patients depended on reliable supply, proper education, and medical oversight. Insulin was not a one-time intervention but a lifelong management tool for many. Its success shifted the focus from rescue to sustained care. His story also highlights how medical breakthroughs ripple through society. Life expectancy for people with diabetes increased. Families reorganized expectations. Healthcare systems adapted to long-term treatment rather than short-term crisis. A biochemical insight in a laboratory influenced demographics and public health planning. Such broad effects are rarely visible at the moment of discovery. Banting remained closely connected to clinical realities. He continued medical work and research, carrying with him the perspective that science serves patients. His demeanor was often described as modest and direct. He did not cultivate a grand public persona. Instead, his reputation grew from the tangible impact of insulin itself. Any sense of regret associated with Banting was subtle and human rather than dramatic. He reportedly felt the weight of responsibility and the pressure surrounding such a consequential therapy. Seeing how many lives depended on consistent insulin availability could be sobering. Success in medicine does not end a story. It begins a long commitment to safe use and improvement. The broader lesson from insulin's history is about persistence and translation. Many scientists had studied the pancreas before, but turning knowledge into treatment required timing, method, and determination. Banting's contribution lay in pushing an idea into practical testing and staying with it through difficulty. Innovation often depends as much on resolve as on inspiration. From a calm historical perspective, insulin stands as one of the landmark medical advances of the 20th century. It did not eliminate diabetes, but it redefined it. That redefinition changed millions of lives across generations. Few therapies so clearly separate a before and after in patient survival. Banting's legacy therefore connects laboratory reasoning with bedside impact. He represents the physician-researcher who bridges theory and care. His work shows how understanding physiology can lead to life-preserving treatment when guided by persistence and empathy. The narrative closes quietly. A doctor pursued a difficult idea, a team refined it, and a therapy emerged that allowed people to live where they once would have died. In that arc lies the steady power of medical science. Discovery, when joined with responsibility and access, can reshape the meaning of a diagnosis. Insulin became not just a drug but a lifeline, and Banting's role in its origin secures his place in the careful, cumulative story of healing. Geoffrey Hinton and deep learning. In the late 20th century, computer science was steadily advancing, but artificial intelligence remained a field of mixed expectations. Early optimism in the 1950s and 1960s had suggested that machines might soon replicate human reasoning. Yet progress proved slower and more uneven than many predicted. Traditional AI relied heavily on symbolic rules and handcrafted logic. These systems could perform well in narrow tasks but struggled with perception, ambiguity, and learning from raw data. By the 1970s and 1980s, parts of the research community had grown cautious, and funding cycles reflected that uncertainty. Geoffrey Hinton belonged to a smaller group of researchers who believed that intelligence might emerge from learning systems inspired loosely by the brain. The idea of artificial neural networks already existed, but it was not dominant. Many scientists considered neural networks impractical because early versions were limited by computing power and training methods. Hinton, however, was drawn to the concept that networks of simple units could collectively learn complex patterns. His interest was not in mimicking biology in detail, but in capturing the principle of distributed learning. Trained in psychology and artificial intelligence, Hinton approached intelligence as a process rather than a fixed program. He was interested in how systems could form internal representations from experience. This perspective set him apart from purely rule-based traditions. He and a small circle of collaborators explored algorithms that allowed networks to adjust internal weights based on error, gradually improving performance. These ideas required patience, because results were incremental and sometimes fragile. For years, neural network research existed at the margins of mainstream AI. Computing resources were limited, datasets were smaller, and training deep networks was technically difficult. Hinton continued refining learning procedures and theoretical frameworks. His persistence reflected a long-term view. If learning from data was central to intelligence, then scalable learning systems would eventually matter. He treated setbacks as part of exploration rather than as final verdicts. As digital data grew and computing hardware improved, conditions began to change. Larger datasets allowed learning algorithms to find richer patterns. Graphics processing units made it possible to perform many calculations in parallel, accelerating training. These technological shifts did not automatically create success, but they removed some practical barriers that had constrained earlier research. A turning point came when deep neural networks demonstrated striking performance in perception tasks such as image and speech recognition. Systems trained on large datasets could identify objects, recognize spoken words, and detect patterns with accuracy that surpassed many earlier methods. The term deep learning became associated with multilayer neural networks capable of hierarchical representation learning. Concepts that had once seemed speculative now showed measurable results. Hinton played a central role in this transition. His research and mentorship helped shape techniques for training deeper networks effectively. He encouraged thinking about representations, how internal layers transform input into increasingly abstract features. This approach aligned well with perception problems, where raw data such as pixels or audio waves must be organized into meaningful structures. As deep learning successes accumulated, industry interest expanded rapidly. Technology companies applied these models to search, translation, recommendation systems, and autonomous systems. AI moved from academic curiosity to commercial infrastructure. Tools powered by neural networks began influencing daily life, often quietly in the background of digital services. With growing impact came broader reflection. Systems that learn from data also inherit patterns present in that data. Questions arose about bias, transparency, and reliability. Deep models could be powerful yet difficult to interpret internally. Their decisions were based on distributed parameters rather than explicit rules, making explanation challenging. Researchers across the field began studying fairness, robustness, and accountability. Hinton himself spoke openly about both the promise and the risks of advanced AI. His concerns were not about current narrow systems alone but about long-term trajectories. If learning systems became increasingly capable, society would need to think carefully about governance, safety, and alignment with human values. These reflections did not reject progress. They emphasized responsibility alongside innovation. Part of his introspection stemmed from seeing how quickly AI capabilities advanced once scaling took hold. Improvements in data and computation sometimes produced nonlinear gains. Developments that once seemed distant arrived sooner than expected. For a scientist who had spent decades advocating neural networks when they were unpopular, this rapid acceleration was striking. It illustrated how foundational ideas can suddenly become central when conditions align. Hinton occasionally expressed a personal tension familiar to many innovators. Contributing to a powerful technology brings pride in the intellectual achievement but also awareness of unintended uses. Machine learning systems can support medicine, accessibility, and scientific research. They can also be applied in surveillance, misinformation, or autonomous weapons contexts. The technology itself is neutral. Applications are shaped by human choices. Still, creators often feel a measure of responsibility for how their work enters the world. Throughout his career, Hinton emphasized curiosity and scientific honesty. He was known for revising his views when evidence shifted. This flexibility is part of scientific maturity. Theories are tools, and tools are judged by how well they explain and predict. His willingness to discuss risks publicly reflected a culture of open inquiry rather than secrecy. Deep learning also reshaped education and research culture. New generations of scientists entered AI through data-driven methods. Interdisciplinary collaboration grew, linking computer science with neuroscience, linguistics, and statistics. The field became both broader and more specialized. What began as a niche pursuit evolved into a major scientific and economic domain. From a historical perspective, deep learning illustrates how ideas can pass through phases of skepticism, persistence, and eventual recognition. Many breakthroughs appear obvious only in hindsight. At the time, they often depend on individuals willing to pursue unconventional paths. Hinton's steady commitment to learning-based models helped keep that path open long enough for technology to catch up. His reflections in later years carry a calm but serious tone. They do not deny the value of progress. They invite thoughtful stewardship. Powerful tools require frameworks for safe use, evaluation, and oversight. The conversation around AI safety and ethics is now a standard part of the field, showing how scientific communities adapt as impact grows. The story does not end with a single discovery but with an ongoing evolution. Deep learning continues to develop, shaped by research, policy, and public understanding. Hinton's role connects early theoretical work to modern applications that touch millions of people. His journey mirrors the broader arc of AI, from speculation to infrastructure, from small experiments to global systems. In quiet reflection, the lesson is about foresight. A researcher follows an idea because it explains something about intelligence. Decades later, that idea helps power technologies embedded in society. The time gap between concept and consequence can be long, but the link remains. Recognizing that link encourages humility. The narrative closes on a balanced note. Deep learning expanded what machines can do, opening new possibilities in science and daily life. At the same time, it prompted deeper thinking about responsibility. Hinton's legacy includes both technical influence and thoughtful caution. Together, they illustrate that advancing knowledge and questioning its impact are not opposites. They are parts of the same scientific journey. Geoffrey Doudna and CRISPR. In the early 21st century, biology was undergoing a quiet transformation. For decades, genetic engineering had been possible, but it was often slow, expensive, and imprecise. Scientists could modify DNA, yet the process resembled delicate surgery with blunt tools. Small errors could derail entire experiments, and altering specific genes in living organisms required time, specialized skill, and significant resources. Many researchers dreamed of a method that would allow DNA to be edited with the same reliability that word processors allow text to be corrected. Geoffrey Doudna's path into this story began with a deep interest in how RNA molecules function inside cells. Trained as a biochemist, she was fascinated by the molecular machinery that reads and interprets genetic information. RNA was once considered only a messenger between DNA and proteins, but research gradually revealed that RNA could also act as a regulator and a catalyst. Doudna's work explored how RNA folds into shapes that allow it to perform precise tasks. This background prepared her to recognize the importance of a curious biological system discovered in bacteria. That system was CRISPR, a set of repeating genetic sequences found in many microbes. For years, CRISPR sequences were known but poorly understood. Gradually, researchers realized they were part of a microbial immune system. Bacteria capture fragments of viral DNA and store them in their own genome. These fragments serve as a memory of past infections. When a virus attacks again, the bacterium produces RNA that guides specialized proteins to recognize and cut the invader's genetic material. It was an elegant defense strategy shaped by evolution. Doudna, collaborating with Emmanuel Charpentier, began investigating how this system worked at a molecular level. They studied a protein called Cas9, guided by RNA to specific DNA sequences. Through careful experiments, they showed that this system could be programmed. By designing a guide RNA, scientists could direct Cas9 to cut DNA at chosen locations. Once cut, the cell's natural repair processes could be used to disable a gene or insert new sequences. What bacteria evolved for defense could become a versatile laboratory tool. When their findings were published, the scientific community quickly recognized the potential. CRISPR-Cas9 offered a comparatively simple, efficient, and flexible method for gene editing. Laboratories around the world began adopting it. Experiments that once took months or years could now be performed more rapidly. Researchers used CRISPR in plants, animals, and human cells. It accelerated studies of gene function, disease mechanisms, and potential therapies. The early atmosphere around CRISPR was filled with excitement. The technology promised advances in medicine, agriculture, and environmental science. It suggested possibilities for treating genetic disorders by correcting faulty genes. Crops could be made more resilient. Disease-carrying insects might be controlled. The sense of entering a new era of biotechnology was widespread. Yet, with that excitement came reflection. Editing genes in living organisms, especially humans, carried ethical weight. The difference between treating disease and altering inheritable traits was not merely technical. It touched on values, identity, and long-term consequences. Doudna became one of the voices urging caution. Her perspective did not reject the technology she helped pioneer, but it emphasized that capability must be matched with responsibility. Part of her concern grew from how accessible CRISPR was. Previous genetic engineering methods required highly specialized expertise. CRISPR lowered barriers, allowing more laboratories to experiment with gene editing. Accessibility is often positive in science, but it also means that oversight and shared norms become more important. A powerful tool in many hands can produce both breakthroughs and missteps. Public attention intensified when gene editing moved from theory toward clinical and reproductive contexts. The possibility of editing human embryos, even for medical reasons, raised global debate. Doudna participated in discussions calling for international dialogue and guidelines. She supported frameworks that would separate carefully reviewed medical research from premature or unethical applications. Her stance reflected a scientist's thinking beyond the laboratory bench to societal impact. There was also a personal dimension. Innovators sometimes imagine how their work might be used, but real-world adoption can move faster and in directions they did not anticipate. Doudna spoke about moments of unease when considering how gene editing could alter future generations. The power to change DNA is also the power to change inheritance. That realization carries emotional and philosophical weight alongside scientific significance. At the same time, CRISPR began delivering tangible benefits in research and medicine. Scientists used it to create better disease models, explore cancer biology, and investigate rare genetic conditions. Clinical trials emerged to test gene editing therapies for certain disorders. Each careful success demonstrated the constructive side of the technology. The same tool that raised ethical questions also offered hope to patients with limited treatment options. Doudna's role evolved from researcher to public communicator and advocate for thoughtful governance. She engaged with policymakers, ethicists, and fellow scientists. The goal was not to slow discovery for its own sake, but to align progress with shared principles. Science, in this view, is part of society rather than separate from it. Its direction is shaped by collective choices. Her career also illustrates how discovery is rarely the work of one person alone. CRISPR's rise involved many laboratories across continents. Still, certain individuals become closely associated with turning points, and Doudna became one of the recognizable figures linked to gene editing's modern era. That visibility brought both recognition and the responsibility to speak about consequences. From a historical lens, CRISPR represents a shift in how humans interact with biology. Reading the genome was a monumental achievement of the late 20th century. Editing it with relative precision marks another stage. Each stage expands agency, and expanded agency requires reflection. The pattern appears across scientific history. Tools grow more capable, and ethical frameworks grow alongside them. Doudna's reflections often carry a calm, measured tone. She acknowledges the beauty of the underlying biology, the elegance of a bacterial immune system repurposed for research. At the same time, she underscores that elegance does not remove complexity from human decisions. Technology can open doors. Society decides which to walk through. The story settles into a balanced understanding. CRISPR is neither a miracle nor a menace by itself. It is a method shaped by intention and oversight. Jennifer Doudna's journey shows how a scientist can contribute to a transformative discovery and still pause to consider its ripple effects. That pause is not weakness. It is part of mature scientific culture. In the broader narrative of discovery and regret, her case is nuanced. The feeling is less about wishing the knowledge did not exist and more about recognizing its gravity. To uncover a powerful capability is to inherit questions about its use. Doudna's legacy includes both the technical breakthrough and the call for careful stewardship. Together, they form a story of innovation guided by conscience, where curiosity and caution move side by side. Stanley Milgram and the obedience experiments. In the early 1960s, psychology was increasingly concerned with understanding how ordinary people behave under authority. The world was still processing the aftermath of World War II, and many struggled to comprehend how large numbers of individuals had participated in harmful systems. Explanations that relied only on cruelty or fanaticism felt incomplete. Some scholars suspected that situational pressures and social structures played a powerful role. Stanley Milgram, a young social psychologist, set out to examine one specific factor: obedience. Milgram's interest was shaped partly by contemporary events, including the trial of Adolf Eichmann, a key organizer of the Holocaust. Public discussion often focused on whether such figures were uniquely evil or disturbingly ordinary. The idea that normal people could commit harmful acts under authority was unsettling. Milgram wanted to test, in a controlled way, how far obedience could go when instructions came from a legitimate-seeming source. At Yale University, Milgram designed what would become one of the most famous experiments in psychology. Participants were told they were taking part in a study about learning and memory. They were assigned the role of teacher, while another person, an actor working with the researchers, played the learner. The teacher's task was to read word pairs and administer electric shocks whenever the learner made mistakes. The shocks were not real, but the participants believed they were. The shock generator in front of the teacher looked convincing, with labeled switches ranging from mild to severe. As the session progressed and the learner intentionally gave wrong answers, the required shock levels increased. The learner, in another room, would protest, express discomfort, and eventually fall silent. If the teacher hesitated, an experimenter in a lab coat calmly urged them to continue, using standardized prompts that emphasized the importance of the research. What surprised many observers was how many participants continued administering shocks despite visible distress. A significant portion followed instructions to the highest levels on the scale. They were often uneasy, showing tension and conflict, but still deferred to the authority figure. The results suggested that obedience to perceived legitimate authority could override personal discomfort and moral hesitation in certain contexts. Milgram did not interpret these findings as proof that people are inherently cruel. Instead, he argued that social structures and roles can strongly shape behavior. In his view, participants entered what he called an agentic state, seeing themselves as carrying out another person's wishes rather than acting on their own responsibility. The presence of a respected institution, formal procedures, and a confident experimenter all contributed to that mindset. The experiments quickly gained attention beyond academia. They touched a nerve because they implied that harmful obedience was not limited to extreme regimes or rare personalities. Under certain pressures, ordinary individuals might comply with troubling instructions. This idea challenged comforting assumptions about moral independence. It suggested that context matters more than many like to believe. However, the studies also sparked controversy. Ethical standards in research were evolving, and critics argued that the emotional stress placed on participants was too high. Some subjects reportedly felt guilt or anxiety when they learned the true nature of the experiment. Questions arose about informed consent and psychological harm. These concerns helped shape stricter ethical guidelines for future human-subject research. Milgram followed up with variations to understand the conditions of obedience. He found that people were less likely to comply when authority was physically distant, when peers refused to obey, or when responsibility felt more personal. These variations showed that obedience is not automatic. It is sensitive to social cues and structures. The presence of dissent, in particular, reduced compliance, highlighting the social nature of moral action. As years passed, Milgram reflected on the meaning and impact of his work. He defended the scientific value of the research but also acknowledged the discomfort it caused. He believed the knowledge gained was important for understanding how societies function and how harmful systems can persist. At the same time, he recognized that the methods forced psychology to confront its ethical responsibilities. The broader cultural discussion connected his findings to real-world hierarchies, military, corporate, and institutional. The experiments became a reference point in conversations about responsibility and conscience. They did not provide simple answers, but they offered a framework for asking harder questions about how authority operates. Milgram's work also influenced how psychologists think about situation versus disposition. Instead of assuming behavior reflects stable character alone, many began to emphasize environmental and social forces. This shift affected not just social psychology but related fields studying organizations, law, and education. There is a quiet, reflective tone to Milgram's legacy. He revealed something uncomfortable about human behavior, the capacity to comply even when uneasy. Yet the same research also implied a path toward resistance. If context shapes obedience, then designing environments that encourage questioning and shared responsibility can reduce harmful compliance. Awareness itself can be protective. In later years, discussions of his work often balanced respect for the insight with caution about the methods. Modern ethical standards would require stronger safeguards. This evolution shows how science learns not only from results but from the process of obtaining them. Each generation refines both knowledge and norms. Milgram's story fits a pattern seen in many scientific journeys. A researcher asks a difficult question, designs a bold study, and uncovers results that resonate far beyond the lab. The impact is double-edged, deeper understanding paired with moral debate. His experiments did not claim that people lack conscience. Rather, they showed how conscience interacts with authority and context. The narrative settles into a measured conclusion. Stanley Milgram illuminated a powerful social dynamic that many preferred not to see. His findings encourage societies to think carefully about leadership, responsibility, and the importance of dissent. The sense of regret sometimes associated with his work is not about the knowledge itself, but about confronting what that knowledge reveals. In that confrontation lies the value of the research, a clearer, if sobering, view of human behavior under authority. Philip Zimbardo and the Stanford Prison Experiment. In the early 1970s, psychology was increasingly focused on the power of situations to shape human behavior. Social unrest, debates about authority, and questions about institutional power were part of the cultural background in the United States. Researchers were trying to understand how ordinary people adapt to roles within systems such as schools, the military, and prisons. Philip Zimbardo, a psychologist with a strong interest in social influence, wanted to explore how environments and assigned roles could affect actions, identity, and moral judgment. At Stanford University, Zimbardo and his team designed a study that aimed to simulate aspects of prison life. The goal was not to replicate a real prison in full detail, but to observe how individuals might internalize the roles of guards and prisoners. The researchers recruited healthy, psychologically screened volunteers and randomly assigned them to either role. Random assignment was important because it meant differences in behavior could not easily be explained by personality alone. A mock prison was built in the basement of the psychology department. It included small cells, barred doors, and controlled access. Participants playing prisoners were even arrested at their homes by local police to increase realism. They were given uniforms and identification numbers. Those assigned as guards wore uniforms and reflective sunglasses, which reduced eye contact and added a sense of distance. The structure emphasized role and environment rather than personal history. From the beginning, the atmosphere shifted quickly. Guards were not given strict instructions on how to manage prisoners, only guidance to maintain order without physical violence. Even so, some guards began adopting authoritarian behaviors. They created rules, enforced discipline, and sometimes used psychological tactics such as humiliation or sleep disruption. Prisoners, in turn, often became passive, stressed, or emotionally distressed. Some showed signs of anxiety and resignation within a short time. Zimbardo acted as the prison superintendent, a role that placed him inside the simulated system as well as above it as a researcher. This dual position later became one of the most discussed aspects of the study. As superintendent, he was involved in maintaining the prison environment. As a scientist, he was supposed to observe objectively. The overlap blurred boundaries and influenced how events unfolded. What surprised many observers was the speed of transformation. The study was planned to last 2 weeks, but intense dynamics emerged within days. Some prisoners experienced strong emotional reactions, including crying and acute stress. A few had to be released early. The guards, meanwhile, varied in behavior. Some remained measured, others became increasingly controlling. The situation itself appeared to encourage certain patterns. The experiment was stopped after only 6 days. A key moment came when an outside observer questioned the ethics and emotional toll of the situation. This prompted Zimbardo to reassess the study and end it. The early termination became a central part of the story, highlighting how immersive the simulation had become and how real its effects felt to participants. When the results became public, the study drew widespread attention. It seemed to demonstrate how roles and environments could push ordinary people toward behaviors they might not otherwise choose. The findings aligned with a broader movement in psychology emphasizing situational forces over fixed personality traits. The idea that context can shape conduct in powerful ways resonated with discussions about prisons, military settings, and institutional authority. However, the experiment also faced significant criticism. Ethical concerns were prominent. Critics argued that participants experienced psychological harm and that safeguards were insufficient. Questions were raised about informed consent, the right to withdraw, and the responsibility of researchers to intervene. These debates contributed to stronger ethical standards in psychological research, including clearer oversight and review boards. Methodological critiques also emerged over time. Some scholars questioned how much the results could be generalized. The sample size was small, and the setting was artificial despite its realism. Others pointed out that participants might have been influenced by expectations about how guards and prisoners should behave. The presence of researchers and the cultural climate of the era may also have shaped actions. Zimbardo later reflected extensively on the experiment and its implications. He did not deny the ethical controversies. Instead, he often framed the study as a lesson in how easily situations can exert pressure on behavior and how important it is to design systems that protect human dignity. He spoke about the Lucifer effect, a term he used to describe how good people can engage in harmful actions under certain conditions. His message emphasized awareness and prevention rather than blame alone. Part of the reflection involved recognizing how roles can capture not only participants but also observers. Zimbardo acknowledged that his involvement as superintendent affected his perspective during the study. This admission became an example of scientific self-examination. Researchers are not outside the systems they study. They can be influenced by them too. The cultural impact of the Stanford prison experiment extended into education, media, and public policy discussions. It became one of the most widely cited psychological studies when discussing authority, conformity, and institutional power. Even critics who challenged its methods often agreed that it raised important questions about how environments shape behavior. Over the years, psychology as a field moved toward stricter ethical frameworks. Institutional review boards, participant protections, and debriefing standards became more robust. In this sense, the controversies surrounding the experiment contributed to reform. Scientific progress sometimes includes learning from discomfort and revising practices. Zimbardo's legacy is therefore complex. He is remembered both for a striking demonstration about situational influence and for a study that pushed ethical boundaries. The sense of regret associated with the experiment is tied less to the question it asked and more to how the study affected those involved. It serves as a reminder that human research carries responsibility alongside curiosity. The story settles into a calm, reflective understanding. The Stanford prison experiment suggested that behavior is not shaped by character alone, but also by structures, roles, and expectations. It encouraged societies to think about how institutions are designed and monitored. Systems can either amplify harm or support humane conduct depending on their rules and culture. In the end, Philip Zimbardo's work stands as a cautionary tale within science itself. It shows how powerful ideas can emerge from bold experiments, and how those experiments must be guided by care for participants. Knowledge about human behavior is valuable, but the process of gaining that knowledge matters deeply. The experiment's lasting lesson is not only about prisons or authority, but about the responsibility that comes with studying the human mind. Hofmann and LSD. In the first half of the 20th century, chemistry was rapidly expanding the boundaries of medicine. Laboratories across Europe were searching for new compounds that could treat illness, ease pain, or support mental health. Many discoveries came not from grand theories but from careful, methodical exploration of molecules derived from nature. One such place of research was the pharmaceutical company Sandoz's laboratories, where scientists studied compounds extracted from plants, fungi, and other natural sources in hopes of developing new drugs. Albert Hofmann was a chemist with a deep appreciation for natural substances. He was particularly interested in alkaloids, nitrogen-containing compounds that often have strong biological effects. His work included studying ergot, a fungus that grows on rye and had a long, complicated history in medicine and folklore. Ergot derivatives had been used in small, controlled doses for medical purposes, especially in obstetrics. Yet they were also associated historically with poisoning when consumed unintentionally in contaminated grain. In 1938, while investigating ergot compounds, Hofmann synthesized a molecule known as lysergic acid diethylamide. It was the 25th substance in a series, which is why it was labeled LSD-25. At the time, it did not seem particularly remarkable. Initial testing suggested little practical effect for the pharmaceutical goals being pursued. As a result, the compound was set aside, and Hofmann moved on to other work. Several years later, Hofmann felt a curious pull to revisit LSD-25. He later described having an intuitive sense that the compound deserved another look. In 1943, he resynthesized it. During this process, he accidentally absorbed a tiny amount, possibly through his skin. Soon after, he noticed unusual sensations: restlessness, vivid imagination, and altered perception. The experience was mild but distinct enough to stand out from ordinary fatigue or distraction. Intrigued, Hofmann decided to conduct a careful self-experiment a few days later, taking what he believed to be a very small dose. He did not yet know that LSD is active at extremely low quantities. The effects were far stronger than expected. He experienced intense changes in perception, thought, and mood. Colors seemed brighter, shapes more fluid, and his sense of time shifted. Because of wartime restrictions on vehicles, he traveled home by bicycle while the effects grew stronger. An event later remembered symbolically in the history of psychedelics. Hofmann approached the experience with the mindset of a scientist. He observed, recorded, and tried to remain calm. After the peak passed, he recognized that LSD had extraordinary psychological potency. From a research perspective, this made it valuable. A substance that could reliably alter consciousness at tiny doses offered a new way to study the mind. Sandoz began distributing LSD to researchers under controlled conditions so psychologists and psychiatrists could investigate its properties. In the 1950s and early 1960s, LSD attracted serious scientific interest. Some therapists explored whether it could help patients access memories or emotions in psychotherapy. Others studied it as a model for understanding psychosis, since it could temporarily produce unusual perceptions and thoughts. During this period, LSD was primarily a research substance, handled in clinical or academic settings. The cultural landscape shifted in the 1960s. Outside the laboratory, LSD became associated with the counterculture, artistic experimentation, and social change. Public figures and movements promoted its use for personal insight or spiritual exploration. Media coverage grew, often emphasizing dramatic or sensational aspects. As recreational use spread, so did concerns about safety, unpredictable reactions, and social impact. Hofmann watched these developments with mixed feelings. He had discovered a powerful compound with potential for psychological research, yet its public image was becoming controversial. He did not see LSD as a casual drug. In his view, it was a potent substance that demanded respect, careful setting, and serious intention. He sometimes referred to it as a medicine for the soul, but by this he meant a tool for insight under proper guidance, not a party substance. As regulations tightened and many countries restricted LSD, scientific research became more difficult. Promising lines of study were paused or ended. Hofmann expressed regret not about discovering LSD itself, but about how widely and carelessly it was sometimes used. A discovery in chemistry had moved into culture faster than systems for education and control could manage. This gap between scientific context and public adoption shaped much of his later reflection. Despite controversy, Hofmann remained a measured and thoughtful voice. He emphasized responsibility, preparation, and respect for the mind. He believed that powerful psychoactive substances should be approached with caution and ideally within structured, therapeutic, or spiritual frameworks. His perspective was not alarmist. It was careful. He recognized both the risks and the potential value. Late in his life, interest in psychedelic research slowly re-emerged in some scientific circles, under strict regulation. Researchers began again to examine whether such substances, used in controlled environments, might help with certain psychological conditions. Hofmann lived long enough to see a more balanced conversation returning, one that separated careful research from uncontrolled use. His story is unusual among scientific discoveries. Many chemicals affect the body, but few so directly and profoundly influence consciousness. LSD highlighted how small molecules can interact with the brain in complex ways, revealing how delicate and powerful neurochemistry can be. For science, it opened questions about perception, cognition, and the biological basis of experience. The emotional tone of Hofmann's later reflections was calm and nuanced. He did not frame his discovery as a mistake, nor as an unqualified triumph. Instead, he saw it as a reminder that knowledge carries responsibility. A chemist can create a molecule, but society decides how it is used. When a compound affects the mind, that responsibility feels even greater. In a broader sense, his journey illustrates a recurring theme in the history of science. Intention and outcome do not always align. A substance synthesized in a pharmaceutical lab for medical exploration became a cultural symbol far beyond its original purpose. The path from laboratory bench to society can be unpredictable. The narrative settles into quiet balance. Albert Hofmann revealed a doorway into the chemistry of consciousness. His work contributed to science's understanding of the mind, even as it sparked debate and caution. The sense of regret sometimes linked to his name is gentle and reflective, less about wishing the discovery undone, and more about wishing it handled with greater care. His legacy combines curiosity, humility, and reflection. He remained, above all, a scientist who respected the power of the substances he studied. In that respect lies the enduring lesson of his story. Discovery expands what is possible, and wisdom guides how that possibility is used. Ending. Thank you for watching. If this story made you think, support the video with a like and subscribe for more thoughtful science stories. Share your perspective in the comments. Your thoughts and reflections matter here. And if you found this episode interesting, send it to a friend who enjoys deep, meaningful topics.